Okay, so we're basically going to study about intermediate code generation, right? So, what is intermediate code generation? I have discussed about this in the very first class as well. So, it is form of a code that is similar to the output code that your compiler generates, right? So, your compiler generates assembly code, right? Then the assembler takes that assembly code and converts it into a machine code. So this intermediate code has various forms. One of the form is three address code. So this three address code is similar to your assembly code. Okay. So what is the benefit of intermediate code, right? What is the purpose of intermediate code? So suppose you have few languages like Python, C, Java, right? So these are the languages. Okay? Like, and you have two systems. Suppose you have Windows OS, you have Mac OS, and you have Linux. So if you want to build a compiler for every if you want to build a compiler for every language for every specific machine, suppose you want to build a compiler for Windows machine that can compile, let's take C here instead of Python, that can compile C language, right? And you also want to build a compiler that can run on Windows OS that will compile Java language, right? And you also want to build a compiler that runs on Windows OS for C++ language, right? Similarly, you want to do that for Mac OS and Linux as well, right? So, how many compiler would you need? You need at least 3 into 3, about 9 compilers that can run each language in each operating systems, right? But what is the benefit of having intermediate code? That you can generate for all for C language, you can just generate one intermediate code, right? And you can convert this intermediate code for Windows OS, Mac OS, and Linux, right? But we're still mm, having to build a three backend of a compiler for running those programs. But if you add more languages, for C you make intermediate code, for Java you make the same intermediate code, for C++ you make the same intermediate code. Now you transfer those intermediate code for different kind of OS system. So for these three language you only need to build three parsers that will parse your language and generate intermediate code, and from this intermediate code you need to uh, build machine code generation module for different operating systems for Windows, Mac, and Linux. So you only need three module to convert your intermediate code into system code. So these three modules are known as backend modules, and these three parsers are known as front-end modules, right? So as you can see, from needing to build 9 compilers, we just need to make three front-end compilers and three back-end compilers, right? For three front-end modules of a compiler and three back-end modules of a compiler. Now imagine if you have like 1000, suppose you have 100 languages and you have 100 machines, right? So you would need to make around 10,000 compilers. But instead, now you only need to make 100 front-end modules and you need to make 100 back-end modules, because they will generate same intermediate code. Okay, so this is known as cross compile, cross compilation, right? So that is why we divide compilers into intermediate steps. One step might parse, or it checks the type, or it checks the static of your compiler, and it will generate intermediate code. So this is known as the front end of a compiler. If you remember from the first class, we have learned about the components of a compiler. You had a front end part and you had a back end part, right? So this is also known as synthesize and analysis part. Okay, and your backend part is the code generator, the targeted code generator that takes the intermediate code and generates into the targeted code. Okay, so these three parts of the front end, the parser, the static checker, or the intermediate code generator, can be simply bundled into one thing, which is a parser. So during parsing, you can make the static checks, okay, and you can also generate intermediate code. Okay, so you see that you can also generate intermediate codes from while parsing. Okay, so that is basically your uh, report, right? So you need to write some algorithm of a code that includes for loop, that includes some variable declaration, for loop or while loop, or and it has some kinds of branching if else statements, right? So with these three things in your language, you need to convert those into a tree address code. How will you do that? You will do that by a parser. So while you are parsing, you will apply the intermediate rules, or you will apply the semantic rules into your parser, and you will generate intermediate code. So you can see all those three parts can be separate as well, or these three things can be bundled together into a parser. So we have already seen while parsing we can also check for types, right? So when we are assigning a value to some variable, we will check what is the data type of that variable. So suppose, right, so your static checkers basically checks that you have a variable which has an integer type and you have some expression. This expression is adding a float with an integer. That is fine, you can add a float to an integer, it will give you a floating point number. But you are adding that floating point number, you are storing that floating point number into a variable which was integer. Integer has 4 bytes and floating point needs 8 bytes of space. So it is not possible to assign a floating point number into an integer variable. Also, you cannot add a floating point number into a string. That is not possible. So you will get an error here as well. Okay. So that your static checker basically checks the type of what you are assigning, right? It also checks for other things. Suppose Are you familiar with the break statement? Can anyone tell me what does the break statement do? Right. So the break statement will take you out of the loop, right? Or if you have a switch case statement, it will take you out of that switch case statement. So the static checker also checks by in your code if this break statement is enclosed. This break statement should be enclosed in some scope, right? So it checks if this scope is for loop, okay, or is it for a while loop, okay, or is it for a switch case statement, okay. So if it is in neither of these three, it will give you an error. So these are the many checkings of your static checkers. It checks for type, it checks for if your syntax is properly semantically correct or not, right? So these are the things. So we have already seen that you can check the type if the type is correctly acquired into the parser as well while you are parsing. Also you can generate intermediate code while parsing as well. We'll see that in the next class, okay. So now let's look at what are intermediate code generation. So as I have said earlier, intermediate codes are basically like the codes that are outputted by your compiler. The compiler outputs a targeted code that might be similar to machine code or that might be similar to assembler, right? Assembly code. So your three address code is basically one form of intermediate code that is very similar to assembly language, right? Or the assembly code. There are other types of intermediate codes as well, right? One of them is known as DAG. DAG is basically directed acyclic graph, and we use DAG. DAG is basically same as your syntax tree, but we have seen that in your syntax tree, suppose you have a grammar and you have some syntax tree, right? Right. So you have already seen that. But in your syntax tree, one node only has one parent. So this node, it has a parent, this, right? So one node can have only a single parent. But in DAG, a node can have multiple parents. And why is that? DAG can have multiple parents because the DAG is used for representing expression that has repeating values, right? So let's look at this expression. Here a is being repeated. Here this sub expression b minus c is also being repeated, right? Okay. So this b minus c is also being repeated. Here a is also being repeated. So we can similarly construct a DAC for this. So let's take b and c. So here we are taking b and c and we are assigning it to a minus node. So this b and c is assigned to a minus node. Okay. So here if you look, this b and c is being multiplied with d. So here you can see the b and c is being multiplied with d. So we take the value. So this node stores the value of b minus c. Okay. So this value is being multiplied with d. So we take a node, we take a multiplication node and we assign it to b minus c and d. So this part is completing this part, right? We also have b minus c multiplied with a. So we can see this b minus c is multiplied with a, right? And this is added with another a. So this whole value this whole value, this b minus c into a, this whole value is added with a. So we add this value is added with a. So we add this with a. So here you can see, after doing this part and after doing this part, so after doing this part and this part, we're simply taking those two value and adding them, right? Because we have a plus between them. So here you can see that this this node has two parents. One is this one and another is this one. Also, this a has two parents, right? One is this one and another one is this one. So DAC can have multiple parents because it is used to, it is constructed by using repeating sub expressions, right? So this is one of the three address representation of your code, right? But it gets trickier to explain, to like construct DAC for complicated operations or complicated codes, right? You just have an expression, so it is easier to use DAC. So what you're gonna do when you have codes like that contains branching, or code that contains for loop, while loop, right? So these will be complicated to represent with that. So that is why we're going to use three address code. Okay, so here is another code. You can read it on your own. So this is basically a grammar rule for constructing directed acyclic graph, right? So these are the semantic rules. This is basically a grammar for expression. So this is basically a grammar for expression, and while you are parsing it, you can use these semantic rules to construct a DAG. So as you can see, these three parts can be added into a parser, right? So when you are parsing, you can check for static checking. You can also generate intermediate code. You can generate intermediate code by either using DAG or three address code, right? So you can do all this while parsing. Okay. Sometimes you need to parse two times to get the proper value for your three address codes, right? You'll see that in later steps, because while parsing you need to keep track of the symbol table as well, and later you need to parse again to get values from those symbol table. Okay, so sometimes you need to parse two times if they are bundled together. Okay, so here is another part saying how DAGs are represented as a data type, right? So you can store DAGs into an array of records. Suppose this is a DAG. This represents I equal to I plus 10, right? So this represents I equal to I plus 10, right? So we can create a array of record. So inside record you have you have multiple fields, right? So every record here has either two fields or three fields, right? So here let's look at the leaf node, which is I and 10, right? So for index 1, we'll have a record which consists of only one field which is an identifier, and sorry, it has two fields, and name which is an identifier, and a pointer which points towards the symbol table entry of I. So wherever the I is put inside the symbol table, it will point towards that memory space. Okay. The second one is an array. The second index of the array is basically another record which consists of two fields. One is a token type, which is a number, and another is the actual value of that number. What is the actual value of that number? The actual value of number is 10. So these are the leaf nodes, right? Now we have internal nodes or the composite nodes. So the leaf nodes will always contain values. Those can be identifiers or the actual values. Okay. So by going for this identifier I, if you want to find the value of I, you can just go to this entry to the symbol table and find the value from the symbol table. Okay. But the internal nodes are the composite nodes that calculates those values, that calculates those expressions. Okay. So how? So suppose this plus, we can keep it in the third index, and we can take it as a three field record. So one field is for the operator, and another two fields are the for the operand. So the plus operator has two operands. So this is the plus operator, this is operand 1, and this is operand 2, right? So one operand is I, another operand is 10. See here, you see 1 and 2. Why 1 and 2? 1 because it is the first index of the array, the id is in the first index of the array, and 2 because this is a number, right? So 2 is in the second index of the array. So this is how you can store the plus. Also we have equal sign, right? So it says I is equal to I plus 10. So here we have equal sign. Equal sign also has two operands. So operand 1 and operand 2. So you're assigning a value, you're assigning the value of operand 2 into the value of operand 1. So here you're assigning the value of I, which is stored at 1, equal to the value of I plus 10, which is stored at 3. Okay. So you can store that. So computers cannot actually draw diagrams, right? So they will store it in this type of data structure. Okay. Now let's talk about the three address code. Okay. So three address code is basically known as three address code because it has three addresses in its expression. But expressions are generally like this. You have an assign operator, and at the left side of assign operator you have a temporary variable or a variable, and the right side of the assign operator you have some operator with some operands, right? So here you can see, if you take this as an example, if you take this as an example, you can see it only has three addresses. This is an address, this is an address, this is an address as well. So these are the variables, right? And variables are stored in some addresses. So that is how it got the name three address code. So in your three address code, along with assign operator, you will only have one operator at the right hand side of your assignment operator. You cannot have multiple operators here. So you cannot have a z plus something, right? Because you'll need some other address or some other variable, suppose z plus c. So this now is equal to 4 addresses, right? So this cannot be considered as a 3 address code anymore. Okay. So in 3 address code, there is at most one operator at the right side of an instruction. So if this is an instruction, there can be at most one operator at the right side of the instruction. There cannot be more than one operator. That means there cannot be any built up arithmetic expressions. So what are the built up arithmetic expressions? It's like this: x plus y into z plus c plus a minus b, right? So these are the built up arithmetic expressions. Okay. So this is basically your 3 address code. And if you look at this 3 address code, you can see these are very similar to your assembly code, right? And these are very similar to your assembly instructions. And what is the benefit of constructing 3 address code? The DAG representation might not be always helpful, right? But the 3 address code representation is helpful in a sense that by looking at this expression, you can easily tell which registers you can use to calculate this value, or which registers you can use to store this value, right? Or which registers you can use to get the values or load the values from these variables, right? So these are very easier to understand, and these are very low level languages, right? And similar to your assembly languages. So here is a 3 address code representation, right? So suppose we want to use the same expression. Okay, so we want to use the same expression to build 3 address code, right? So here you can see this value is common, right? So we can create a variable. This is known as temporary variable. Okay, so these are generated by your compiler. Okay, so we are creating a temporary variable to hold the value for b minus c. We cannot add any more expression to it because we have already used one operator, right? Here you can see this t1 is saved as b minus c. Okay, now we again have a b minus c into d. Okay, so we can create, so we're going to hold the value of b minus c into d into another temporary variable, which is t2, right? So we need to multiply b minus c with d. So we need to multiply b minus c with d. But as you can see, this b minus c is already stored into t1, right? So again, you can see we're only using one operator here. We're only using one operator here to calculate this expression b minus c into d, right? Then again we need to multiply a with b minus c. So again our value is stored at b minus c is stored at t1. So we take another temporary variable which is t3, and we add it and we multiply it with a. So t1 into a, right? Now we need to add this value which is saved at t3 with a. So we need to add this with a. So let's take a new temporary variable which is t4, and let's add this to a. So t1 t3 plus a, because this whole value is saved at t3. So t3 plus a gives us new variable which is t4, which is this one, a plus a into b minus c, right? And we also have b minus c into d, which is saved at t2. So to compute the whole expression, we take another variable which is t5, and we say t4 plus t2 gives us the whole expression, and that is saved as t5, right? So this DAC can be represented as this three address code. Okay. And further, if you remember, compiler also had a code optimization part, right? So you can further optimize this code as well, right? Okay, so the generated three address code might be different from the book because of the temporary variable names, but it has the same functions. Okay, so you need to remember few things about the three address code. The three address code has a name. Basically, a name can be a variable, right? For example, this b and this c and this d and this a, right? So these names are basically your variables. Okay, so three address codes can have names. Along with names, the three address code can have compiler generated temporaries. So these temporaries are basically a temporary variable that stores some value. These variables are your compiler generated variables. So here you can see T1, T2, T3, T4 and T5. These are generated by your compilers. Okay, and it also has a constant. So your three address code can also have a constant. If you remember, we had a DAC for I equal to I plus 10, right? So the three address code of this would be T1 is equal to I plus 10 and Ti is equal to T2, right? Sorry, T1. So we can further optimize this, right? We can just let's keep it here. Uh, we can optimize this as simply I is equal to I plus 10. This is also a three address code, right? So it took us two lines, but we can optimize this into a single line. So here in this three address code, we also have a constant, right? So your three address code will consist of these things. It will have, so এই যে অ্যাড্রেসের কথা বলছে, so we are talking about addresses in our three address code. These addresses these addresses can be a constant. Okay, these addresses can be a variable or name, or these addresses can be a temporary variable which is generated by your compiler. Okay, so these are the three types of addresses in your three address code. Okay, so far have we understood what I have been talking for so far? Is it understood or you have any confusion? Right, these are only expressions, right? So there are no we have not seen any instructions for loops or conditions, right? But we'll see them. Okay, so let's look at this part. So this is basically the important part of today's topic. Okay? So this part talks about how your parser needs to parse two times to get the actual value and all. But here are the instructions that we can use to represent the tree address code, right? So if we look at the first instruction, it is the assignment instruction. So assignment instruction will be like this: x is equal to y operator j, meaning there will be assignment operator, and the left hand side will be one address, and the right hand side will be two addresses with an operator, right? Like for this, for example, i I is equal to I plus 10. So left hand side will have one address, we will have the assignment operator, and the right hand side will have two addresses, I and 10, and it will have one operator. It can be an arithmetic operator. Okay, so plus. So this basically means we calculate this part, we get the value, and we store the value in this address, right? We add those values in this address. We calculate the values using the operator of these addresses, and we store that value into this address. Okay. Second one is the assignment operator in form of unary operation. So what is the unary operation? Suppose I is equal to minus I. That means whatever the value of I is, multiply it by minus 1 and store it inside the address of I. Okay, or it can be value of minus 10. So this is an address. This is one operator that has only one operand, and we calculate this and store it into this address. Or it can be a binary operator, shift, shift left, right, shift right, right. So these are basically unary operators. Okay, that has only one operator. Three address code can be in form of copy instructions, like x is equal to y, where x is assigned the value of y, like a equal to b. Here the value of this address will be assigned to the value of this address. There could be an unconditional jump, like go to L, right? The three address instruction with the label L is next to be executed, meaning we have seen the conditional jump and unconditional jump in microprocessors, right? So when you say go to and you give it a label, that means it will directly jump into that label without checking anything. Okay, and whatever label it has, suppose there, this is known as label L, right? So when compiler sees this instruction, it will directly jump to this label and start executing this instruction. T is equal to b minus c. Okay. Okay. Conditional jump in form of, কিছু বলবেন? হ্যাঁ, লুপ করার জন্য ইউজ করতে যেতে পারে। তারপরে হচ্ছে আপনার ব্রেকের জন্য ইউজ করা যেতে পারে। তারপরে হচ্ছে ইফ এলস এর জন্য ইউজ করা যেতে পারে, রাইট? সো আনকন্ডিশনাল জাম্প, conditional jump. Conditional jump is in the form of, if you have some address or you have some expression then go to L. Or you have if false, meaning this condition is not true, go to L, right? Meaning if 0, or you get a value which is always true, right? You go to, sorry, if 0 means it is false, go to some level, and you say if false, and you give some value, this is true, right? So true is not false. Okay, so if you give this if 0, if false, meaning whatever the value here is false, if that is false, then it will go to this label L. So it will go to this label L here, because so in binary 0 is equal to false, 1 is equal to true. Okay, so suppose it is like this. So this is your 3 address code. Okay, now look here. After executing this line, it says if 0, go to L, meaning if this expression or this address is true. Okay, so constant is also an address. If this address is true, then you need to go to L. So is 0 true? No, 0 is false. So if it is false, you will execute this line. Okay, you will execute the next line. So if this is false, if this is false, this value here is false, you will execute this line. But if instead of 0 you had 1 here, right? You had 1 here, so it will be true, and you need to go to else. So you need to execute this line here. Is it clear? Okay. So if false is exactly the same. Instead of if you had if false, that means whatever the value we have after it, if it is false, you will go to that label. If it is not false, you will go to the next line. So 0 is false, right? So if false, so the next one is false, so you need to go to the label L. But if you had 1 here, meaning is the next thing false? No, this is true, right? So you need to go to the next line and execute t is equal to d plus 8. Now we have conditional jumps. So these are conditional jumps. Similarly, for if and if false, we can also use it. So instead of just one value, we'll have this expression, right? বেটার হয় আমি এক্সেলে দেখা। So this is your level 1. Okay, so this is your three address code. So this relational operator can be greater than, can be less than, can be equal to, can be less than equal to, can be greater than equal to, right? So all the relationship operator can be here. So not equal to, right? So if this expression is true, if this part is true, then it will go to this line. It will execute this line. And if it is not true, it will execute the next line. Okay? And if you give if false, meaning if this expression is true, okay, then it will execute next line. And if this expression is false, okay, then it will execute this line. Clear? না, লাইক সামনে যে এক্সপ্রেশনটা থাকে ওইটা যদি ফলস হয় তাহলে জাম্প করবে, আদারওয়াইজ পরের লাইন এক্সিকিউট করবে, সিম্পলি বলতে গেলে। জাস্ট ইফ আর ইফ ফলস, মানে এটাকে আপনি আপনাকে ইফ এলসে কনভার্ট করে নিতে হবে। আপনি তো অ্যাসেম্বলি ল্যাঙ্গুয়েজ করছেন, রাইট? আপনি যেভাবে অ্যাসেম্বলি ল্যাঙ্গুয়েজকে কম্পেয়ার করে হচ্ছে ইফ এলসে কনভার্ট করছেন না লেভেল দিয়ে, সেম ওয়েতে করতে হবে। So these are for procedure calls. If you want, you can read them. So it is also in section 6.9, but that is not in our syllabus. Okay, and that is for, and this one is for array. Okay, so this one is for array. It basically means you are assigning the value of ith index of y into the value of x, and you are assigning the value of y into the ith index of x, and whatever the value it has, that index has, you are assigning that value to that index. Okay, and also here is the part for pointers and addressing, right? So this l value means location value, and the r value means the actual value. Okay, so if you want to read it on your own, you can. So let's see, suppose you have a variable x is equal to 10. You have this instruction, right? So this l variable x has address value, so it can be at address 0x112 uh, a 112 a to c b 4 hex value, right? So this x can be located at this memory location, right? And the r value of this x is basically 10. Okay, so this is the r value and l value. Okay, now let's look at an interesting thing. Okay, so here you see you have a code which says do I is equal to I plus 1 while this condition is true. This is basically do while loop. Okay, so if you remember, if you learned about do while loop, this is basically a do while loop, meaning first you will execute this instruction I is equal to I plus 1 no matter what, no matter if this condition is true or false, does not matter. You will first execute this line, and after that you will check if this condition is true. If this condition is true, then you always need to execute this expression, and after that you need to check again if this expression is again true or false. Okay, so this is basically do while loop. So how can you convert this into a three address code? So if you look here, it talks about, for addressing, it talks about the ith location memory unit beyond the location y. So let's understand this. So suppose, right, so we need to assign the value of ith index of y. Suppose y is an array, right? Suppose the value of I is set as 3. Okay, and right, so you have an integer array that has these variables: 10, 20, 30, 5, 52, and 80. Okay, now you have set the value of I is equal to 3, and you are assigning I y is equal y of I is equal to x. So what is the value of x? Obviously the value of x is this 5, right? So I of 3 is this index, and the value of x is the value of this index, which is 5. So value of x is 5. But how does it calculate? So this is y. It has a starting address. The address of y, suppose, is 200, right? And we know this is a integer array. So each integer takes 4 bytes of space. Okay, so this address is basically 200. This address is basically 204, right? And this address is basically 208. This address is basically 212. This one is basically 214, and 216, and so on, right? So how does it calculates that it needs to assign the value at address 212 with to the value of x, right? How does it calculate? So it takes the value of y, so it takes the value of I, which is 3. So the value of I is 3, and it multiplies it by 4. Why 4? Because each index takes 4 bytes of space. So this is 3 into 4, we get 12. Okay, and how it gets this address, to, to 212? It simply adds the address of y with the address of I into 4, which is 12. So it basically gets 200 plus 12. So it gets the address 212, and it assign whatever value is inside this address, which is 5. It assign that value to this variable x, right? So whenever we're dealing with indexes of an array, we need to multiply that in the 3 address code. Okay, because when we're using this three address code here, when the actual code and the three address code of array is different. So this is your actual code, right? The index of 3. This means the y index of 3, whatever the value is, will be the value of x. But if you use this in the three address code syntax, if you use yi, this basically means y plus I, right? So the value of I is 3, the value of y is 200. So there is nothing in 203. There is nothing in 203. So from 0, from 200 to 203, we have the value 10. But what we actually need, we need the address 212. So for three address code, you first need to multiply it. Okay, multiply it by 4. Right. So now let's look at this code. So this is basically the code, three address code of this translation. Okay. So, so we can save I plus 1 that we need to do into T1, right? And we can save T2, can save I into T1, right? So we need to do this part, or we can just write I is equal to I plus T1. That is fine as well, right? Now we need to check this part. While A of I is less than V, right? So let's do it like this. Now we need to check, we need to first calculate A of I. So we can assume that I is an integer or I is an float. So if you look here in your book, it multiplies with 8 because it assumes that I is a float. Okay. So to calculate this, we are assuming I is an integer. Okay. So let's take another variable which is t2, and we say I into 4, right? So we have calculated this part, bracket I. We have calculated bracket I. I plus 1 করলাম না আমরা, এখানে t1 হবে বেসিক্যালি। ওকে, সো আমরা i প্লাস 1 এটা ক্যালকুলেট করলাম না, এটাকে t1 এ স্টোর করছি, দেন এটাকে তো i এ স্টোর করতে হবে, রাইট? ওই জন্য i ইজ ইকুয়াল টু t1। অথবা আপনারা চাইলে একবারে করতে পারেন, জাস্ট এই লাইন লিখলেই হবে, আর কিছু করতে হবে। ওকে, সো we need to calculate a of I, right? So to do that, you see here it is using this value, this t2 value into the bracket of a, right? So when you are calculating this address, we can take it to another temporary variable and save the value. The value will be a of t2, right? If you give here a of I, that will be invalid. That is not okay, right? Because it will add the value of I to a. But if I is an integer, we need to multiply it by 4. And you cannot do it this like, you cannot do this in one line because this array is an operator itself. So you cannot have another operator inside. So you need to give t2 here, right? Okay. So we have calculated this a of I as t3. Now we say if t3 less than v, go to, if this is true, we need to execute this line, right? T is equal to I plus 1. So we say go to label 1 and we just label it as L1. And if it is false, it will simply go to the next line. So there is nothing in the next line, right? There is nothing in the next line of this do while. So this is how you construct a three address code from an expression that has an array inside it. Okay. So instead of this label, we can use numbers, memory addresses, right? So these instructions are saved in memory addresses. Suppose this t1 is equal to I plus 1, this instruction is saved as memory address 100. So instead of labeling this, we can say just go to memory address 100. If it goes to memory address 100, this rule, this line will be executed. Is it clear? Okay, so we do not have time today. In the next class, we'll learn about quadruples, triples, and indirect triples, the representation of three address code. It will only take 10 minutes. Okay, and after that, we'll start our last chapter. Okay, do you have any questions? If not, I'll stop the recording. Yes, you'll get the enough knowledge, plus you'll need to self study about two more chapters to get to understand the full things. Okay, so I'll stop the recording.